Hi everyone, welcome to another episode of Coast and Climate, my weekly video podcast here on WAFB Plus, or if you're checking it out on our website, WAFB.com. We're into hurricane season now, and obviously a lot of eyes are going to be on the Gulf of Mexico in the weeks and months ahead. Now, there was an article published not too long ago that got a lot of attention talking about the loop current. So I thought maybe it was a good time to bring in somebody who knows a lot about the loop current, what that means for hurricane season and storms, and what we've seen in terms of how it's impacted some of the past storms and hurricanes in the Gulf of Mexico. So the guest that I'm going to bring in today is Dr. Nan Walker from LSU. She's the James P. Morgan Distinguished Professor of Coastal Studies in the Department of Oceanography and Coastal Sciences at LSU, also the Director of the EarthScan Laboratory, and just for full disclosure, she also sat on my PhD committee at LSU, somebody I've known for a long time. So with that, good to see you, Dr. Walker. Thanks for joining me this morning.
It's my pleasure, Steve. Thank you for inviting me.
All right, so let's talk about this. The loop current getting a lot of attention here in recent weeks, and something we'll be paying close attention to as we head on into hurricane season. First thing I wanted to ask you about is, if you can, in simple terms, just explain to people what the loop current is.
Okay, the loop current is a very warm and deep water flow which enters the Gulf of Mexico through the Yucatan Channel. So it's water that's been heated in the equatorial regions, crossing the Atlantic Ocean. And so it enters through the Yucatan Channel. It flows northwards, and somewhere in the middle of the Gulf or closer to the coast, it loops back towards the south and the southeast and becomes the Florida current in the Florida Straits. And it's actually a very integral part of the Gulf Stream system, and that includes the North Atlantic Gyre as well. So it's a very important current in terms of, circulation in the North Atlantic Ocean, and especially in the Gulf of Mexico, because it's our major source of warm water to fuel hurricanes.
Yeah, and you're kind of leading me into my next question there. So what is the significance of the loop current during hurricane season? As a meteorologist, one of the things that I always preach to people is that throughout hurricane season, the Gulf of Mexico is warm enough to support tropical storms and hurricanes, but it goes a little bit deeper than that, both figuratively and literally when we talk about the loop current. So maybe explain a little bit about that.
Okay, sure. So the loop current, I did mention that it's a deep water current. So what does that mean? When I say deep water, I'm talking about a half a mile deep, so very deep. And so it's basically bringing in an unlimited amount of fuel in the upper ocean to rapidly intensify a hurricane. So as hurricanes move across the ocean, they typically bring up colder water. We call this their cool wake or their cold wake. And this keeps them from becoming monster storms in general. But the loop current doesn't have any cold water within the top, say, 300 feet. And so everything that the waves entrain to the surface is going to be warm water. So like I said, we have an unlimited source of heat to hurricanes. That's what the loop current does to hurricanes in the Gulf. So one thing I didn't mention is that we have to monitor the loop current on a daily basis, because it's very dynamic. Sometimes it's close to the Louisiana coast. Sometimes it flows from the Yucatan Channel to the Florida Straits. But when that happens, it's usually shed a lot of its northern part as a warm core eddy. So there's a lot going on in the Gulf of Mexico. It's kind of like a few washing machines with water half a mile deep moving around and interacting, different water masses interacting with each other. But the good news is that it's fairly easy to track with some satellite data that we use on a daily basis.
Since you mentioned that, let me bring up a graphic here, a graphic that you shared with me, and actually comes from the University of Miami. But so in this particular graphic, you see labeled there, oceanic heat content. this is one way we can track the loop current. So explain kind of how we can and what this is relative to sea surface temperatures. People are maybe a little more used to seeing sea surface temperatures and water temperatures. What's the difference between that and this oceanic heat content map?
Okay, so the oceanic heat content maps are created from sea surface height data, which is one of the ways that we track the loop current and the warm and cold core eddies. It indicates that the layer of warm water is very deep relative to the water around it. So not to complicate things, but to explain to your viewers what's going on in more detail, if you look at a sea surface temperature map, in the middle of summer, the Gulf looks quite similar in sea temperature. So maybe about 80 to 86 degrees Celsius. Okay, this is an image from late May from the EarthScan lab. So it's showing sea surface temperature across the Gulf. And at the moment, you can still visualize the loop current as the warmest water in the Gulf of Mexico. But as summer progresses, the water looks more and more similar, but the sea surface temperature is actually masking the changes in heat content in the Gulf of Mexico. So the loop current continues to be the major source of heat content, although you might not distinctly see it at the surface. So it's a little complicated. So in the middle of summer, we have to give up using sea surface temperature to map the loop current. So we use sea surface height. And the ocean heat content map is derived from the sea surface height, which is a better way of mapping the loop current in the summer.
Sure. So in other words, as the name implies, with sea surface temperatures, we're really talking about that top layer of the ocean, what the water temperature is. When you get into the oceanic heat content, we're talking more about, how deep that warm water is. Really important for our tropical systems. So let me ask you about this now. I mentioned at the beginning that there was an article that got a lot of attention from an oceanographer right before hurricane season started. And what he noted was that the loop current, as it stands kind of heading into or now into hurricane season, seemed to resemble some of what we saw in 2005. And that's like, oh boy, that gets people's attention. What can you tell us? Can we make much of that right now? Or is the loop current going to kind of evolve through the season, and does the now not tell us so much about what will happen in the future?
Okay, so that's a lot of right. Questions. All right, so the loop current it's very difficult to predict what's going to happen with the loop current. So far, models have defied prediction of the loop current. The big situation, or the big event with the loop current, is when it sheds a warm core eddy, or when the whole northern loop of the current separates off of the current. And there's a number of factors that go into that. And the reason that it's not easily predicted is that we don't have enough data in the ocean, in the inflow and in the outflow, to model the whole system. But scientists are working on that. Anyway, in terms of the current conditions, so you saw the sea surface temperature map of the loop current a minute ago, and you saw the heat content. So the loop current is fairly well intruded into the northern Gulf. In other words, it's quite close to the northern Gulf coastline. It could be closer. In the case of Ida and Katrina, it was closer to the coastline. And in addition, a warm core eddy was in the process of separating. And I've been studying those in more detail lately. And what happens when they separate, they typically move to the west. And so you're extending the deep warm water into the western Gulf a bit. So you're actually increasing the area of coverage of warm water with high heat content. So actually it's like a worst case scenario when you shed a warm core eddy, and if you still have the loop current also feeding water into the Gulf. And then besides that, sometimes the warm core eddies start to separate and then they don't because the loop current surges north again to recapture them. And that's even worse because that happened before Katrina and also possibly before Ida. We're still working on understanding all that. But it looks like the loop current surged north, which is an additional amount of heat coming from the equatorial Atlantic into the Gulf of Mexico. So it's definitely something that we need to, monitor on a daily basis, because the changes in the loop current can happen very fast.
Since you brought up Ida a couple of different times, and I briefly brought up the graphic that you sent me, I want to bring up this graphic again, though. Tell people a little bit about what we saw in terms of the interaction of the loop current and Hurricane Ida last season.
Okay, so the kind of dark orange tones are the mapping of the loop current, and there's a black line around the edge of the loop current showing you, its spatial extent. So you see in the northern part, it looks like the loop current has actually kind of separated this warm core eddy, which is moving, as I said, towards the Louisiana coast and a bit to the west. Okay, so we have a very high heat content throughout the central and part of the eastern Gulf. So what is annotated here is the track of Ida. So Ida left the coast of Cuba and moved over the loop current. And if you look at the details of the miles per hour that are written on this graphic, you'll see that over the course of it transiting the whole loop current, very unfortunate for us, right, that it flowed over the loop current, it increased from a Cat 1 hurricane to a Cat 4 hurricane before exiting the loop current and moving closer to Louisiana. You might notice that the wind speeds actually continued to increase as it moved off the loop current, probably because there's a bit of a time lag between, when the evaporation occurs, which is the link between the ocean and the atmosphere, and when, full intensity was reached. So did that make sense, or did I forget something?
No, I think you hit it. The only thing, so you give the oceanography perspective, and this is something you and I had talked about behind the scenes from the meteorologist perspective. The oceanic side is very important there, and that deep warm water, but it also takes to get an Ida, Katrina or Rita, the atmosphere's got to be working with the ocean. You've got to have both of those being very favorable to get these very powerful hurricanes. And so I think that's why from some of the meteorological community, when this article came out a few weeks back, and this is a real well-respected oceanographer, I know you know him very well, but there was some pushback from the meteorological side because they kind of felt like this was maybe a little oversimplification of what it takes to get a powerful storm. Because as we said, right, every summer is warm in the Gulf of Mexico. The loop current's always there in some form or fashion. So you've got to have a disturbance or a tropical system moving through, and the atmosphere's got to be working in your favor too to have a strong storm.
Yes, I agree completely. Yes, they have to be working in the same direction. If one's providing positive feedback and the other's providing negative feedback, then chances are you're not going to have a major hurricane. So, and as you say, the loop current is typically, if the loop current isn't fully intruded into the northern Gulf, then there's a big warm core eddy. So we always have a big source of heat in the Gulf of Mexico. But what is important besides the atmosphere is also how the hurricane tracks. Does it track over the loop current? Is it tracking over warm core eddies, cold core eddies? Because we have a whole range of conditions in the Gulf that can affect the hurricane.
So we focus a lot on the storms that intensify and get really powerful over the loop current, like Ida, like Katrina, like Rita, and over some of those warm eddies. But as you just mentioned there are also these cool eddies. And I know in particular you kind of studied the effect of one of those cool eddies with Hurricane Ivan. Some people might remember that one. It was in 2004, made landfall in Alabama. I remember it well because I actually covered that one from Alabama. But tell people a little bit about what you found in studying Hurricane Ivan and the cool eddy.
Okay, sure. Yeah, Ivan was a major hurricane, as you know. I mean, it kind of got dwarfed the next year by Katrina and Rita, but it was, you know, quite an impressive system. All right, so one thing I didn't mention is, besides the loop current and the warm core eddies, which are very important for hurricane intensification, there are cold core cyclonic eddies always along the periphery of the loop current. And when a warm core eddy forms, they actually move with the warm core eddy, so they stay around the warm core eddy. So we have cold core eddies around the warm core eddy. And the cold core eddies are areas, we call them areas of upwelling. So the cold water, which is deep down in the ocean, is closer to the surface. So when a hurricane crosses over a cold core eddy, it mixes up the cold water rapidly to the surface. This does not happen in a warm core eddy or in the loop current because the warm water is so deep. So in the cold core eddy, after Hurricane Ivan passed over the Gulf of Mexico, there were huge, very cold areas of warm water, very pronounced. Like, I'm trying to remember the exact temperature changes. The temperature change was 6 to 8 degrees Celsius, so that's about at least 10 to 12 degrees Fahrenheit. So what happened was these big areas of cooling were observed, and it took us a while to understand them. So what we had to do was combine the sea surface temperature data with the sea surface height data, like overlay the two in an image so that we could understand the dynamics of what happened in that system. So there were two very cold core eddies which intensified as the hurricane moved over them. And the interaction between the ocean and the atmosphere ended up with these big coolings, which actually decreased the intensity of Ivan. Not a lot, but enough so that it wasn't like full strength when it hit the coast. And funny enough, a similar thing happened to Katrina. So Katrina was a Category 5 hurricane leaving the loop current, but there was a cold core eddy which was intensified by the hurricane, bringing cold water up rapidly. And Katrina actually decreased intensity by 2 categories before it hit, at least before it hit New Orleans, maybe the coast. I'm not remembering all those details. And part of that was potentially the cold core eddy. Just to give that whole process some more importance, I've studied a hurricane in the Eastern Pacific, Hurricane Kenneth, also in 2005. And Hurricane Kenneth actually brought up enough cold water to kill itself. So the hurricane died over its own cold wave, which is, we haven't seen any other case like that. We wish it would happen in the Gulf.
Well, and I think
Unlike,
sorry, go ahead and finish what you were saying.
Yeah, that's okay. I think it's all right.
No, so what I think is interesting about Kenneth is it kind of introduces another variable we didn't talk about a lot. We talked about this warm and cool water. We talked about the depth of the warm water. But another variable with Kenneth was the forward motion of the storm, right?
Right. So if the faster the hurricane is moving, the less influence of the ocean. The slower it moves, the bigger influence. So the fact that Kenneth, the large scale circulation determined its rate of movement. So the large scale circulation had it like stopped basically over this cold core cyclonic eddy that it intensified into this monster cold core system, which was at the surface, and the temperatures were way below the temperatures generated by the hurricane were way below what was needed to maintain a hurricane. So essentially it died over, it became a tropical storm. So it changed from a Category 4 hurricane to a tropical storm over the cold wake that it generated. So it was quite an interesting case.
It's a great lesson. It's a great point you make, and it's all about that upwelling that you previously discussed. So those hurricanes, they have so much wind with them, they stir up the water, and the longer they sit in a spot, the more and more they can kind of have that negative feedback on themselves by bringing up that cool water. So I think you've given us a good lesson in some oceanography and the loop current and its eddies today. At the beginning, I mentioned that you're also the director of the EarthScan Lab at LSU. So before I wrap up today, just tell us a little bit about what the EarthScan Lab is and what you guys do over there.
Okay, the EarthScan Lab dates back to 1988, and what it is a lab that specializes in real-time processing and dissemination of satellite data of the ocean and the atmosphere. So we like to think that we're good at monitoring hurricanes, monitoring ocean currents such as the loop current, the warm eddies, the cold eddies. We really have specialized on Gulf of Mexico oceanography and meteorology rather than like a larger area. And so we have 3 antenna systems that have in the past were used to capture the data because there was no other source of data early on in satellite work, satellite meteorology and oceanography. But now, you know, people are very familiar, well, they're accustomed to having data available in real time from other places like NOAA and NASA. They actually have become very good at providing data on their in the cloud or on their web pages in near real time. So we haven't had to, you know, spend all the money to keep those antennas going. So now we pretty much depend on the federal labs to do that. But in the early days, it wasn't like that at all. So we have a very comprehensive archive of satellite imagery on our webpage, and I hope you will visit our webpage and provide, you know, comments to myself or the systems manager or others that you might see linked there. And so basically we keep an archive that dates back to 2000 of SST products, and also the integration of sea surface temperature and sea surface height, so that helps us track these systems in the Gulf. So I hope you will visit us there, and we will look forward to that.
Yeah, so for everybody watching, go check it out. They really do have some great imagery. It's kind of current, and then you can kind of browse through the archive of some neat imagery from the EarthScan Lab as well. Well, Nan, I really appreciate your time today. Thanks again for giving us a little bit of a lesson, and we're hoping this year the loop current doesn't end up being too big of a factor, you know, in terms of any intensifying hurricanes in the Gulf.
Me too. I really am hoping that as well, as everybody is. And thank you for having me, Steve. I enjoyed sharing the little I know about the loop current. It's a difficult system to understand, and always changing.
Well, you're being humbled by saying the little that you know. You know a lot, and I do appreciate your expertise. So thanks again for being here today.
Okay, you're welcome.
All right, folks,
Bye.
so hopefully you learned a little bit about the loop current today and what we'll be tracking in the hurricane season. It's about the combination of the atmosphere and the ocean when it comes to these tropical storms and hurricanes. So hopefully you have a little more insight into how all of that works. So we'll be back here next Thursday with a new episode of Coast and Climate. I'm going to be joined by Marie Constantine with the Louisiana Stormwater Coalition. The Louisiana legislature recently passed a bill that's going to allow for local municipalities to establish these stormwater utilities. And basically, if local municipalities opt in, they will have the option to create these utilities and designate your dollars towards how they address flooding and litter and issues like that. But it's a really interesting discussion. So join me here same time next Thursday at 10 o'clock as we speak with Marie Constantine from the Louisiana Stormwater Coalition. In the meantime, you can watch any of the past episodes on WAFB Plus and on our website at WAFB.com. We'll see you next week.